Everyone, my name is Robert Stanton. I'm a graduate student here at Clarkson in the physics department, working under my advisor, Dr. Dara Trivedi. Today I'm going to be talking about theoretical insights into host-guest interactions of metal-organic frameworks. So I'll start off by talking a little bit about metal-organic frameworks, what MOFs are. They're basically, just generally speaking, these collections of metal ions and oxygen atoms creating these clusters called nodes. And then linking these nodes together, you have organic ligands. So you can imagine these are going to have a wide range of different combinations that you can choose from. Swapping out the metal ion, swapping out the ligand. You can play with how connected the MOF is, so how many connections it has to other nodes. You can change how many connections each ligand has to other nodes. And with this kind of, like I said, wide range of combinations, you can imagine that there are going to be a bunch of different possible applications. So you can see in the diagrams here a bunch of them, but I'll talk about a few that are important for my research. The first one being contaminant capture. So you think of using the actual MOF to remove some sort of harmful chemical from bodies of water or gas. Think of air purification, things like that. Carbon capture. Low concentration contaminant detection is another one, so this would be more along the lines of chemical sensors, so making sure that we can either detect things that are harmful in low concentrations or things that are easier to deal with before they become too large of a problem. Gas storage and separation, and then more recently we've been looking into charge transport for electrochemical device applications, so actually using MOFs to facilitate charge transport for these sort of things. So the importance of this computational work, broadly speaking at least, is that it gives us an atomic view of what's going on. So here you see an SEM image of a MOF, and you're just not going to be able to get the resolution that you can get by employing these computational methods. So they're generally pretty good to complement some experimental work and maybe make suggestions for, small changes that could be made. And really what it does is it allows us to see when we have a functional MOF, what specifically is going on that's making it so good. And that then you can use to try to fine-tune the MOF and make it more efficient down the road. So finding things like binding mechanisms are relatively simple. Site-specific interactions, if you have a MOF that has multiple candidate sites for binding of gas molecules. The analysis of defect-containing MOFs is really important because you can explicitly just put molecules at these defects. Defects in MOFs generally happen during the chemical synthesis. You might have some number of defects per node, and interesting things can happen with the binding there. And then being that the methodology is electronic structure codes, we can have readily accessible to us things like charge density, density of states, etc. So the details of our computational work, we're using density functional theory within quantum espresso. Density functional theory, here we're just employing cone-sham density functional theory using plane wave basis sets. And it can deal with, of course, periodic structures. So if you want to deal with the full MOF, you can do that. Or if you want to deal with, say, just the node, or if you want to see how an interaction is happening at a specific site on the node with a ligand, then you can throw that into a simulation cell, pack it with vacuum to prevent interaction with the periodic image, and then go from there. The reason we're doing this is because these plane wave codes can include things that will describe pretty well dispersion interactions, and these are going to be really important for binding of gas molecules in MOFs. So some of the applications of the computational work, a lot of things we've been doing have just been calculating adsorption energies for contaminant capture. So here you see introduction of phosphate to a cerium-based MOF. Here you're seeing some PFAS introduced to a zirconium-based muff, and then we can determine things like the site preference. Again, we can see what happens when we are removing maybe those weakly bound ligands and determine, again, which sites are preferable, what happens at these missing linker sites, and things like that. So I will wrap it up here. I'd like to say thank you to all of our experimental collaborators, so Professor Silvana Andreescu's group and Professor Mario Reit's group for the cerium muff and zirconium muff, respectively. I'd like to thank Exceed for computational resources, thank Clarkson's Ignite program for partial funding of one of these projects, and then Clarkson University, of course, as a whole, for giving us the platform to, give talks like this at ERAPS and all of the other things that come along with attending Clarkson for school. So, again, thanks for listening, and I will be online to respond to the questions that anyone may have over the couple days that the ERAPS forum's live. Thanks.